Right. Okay. I want to talk about engine lubrication. So in a conventional piston engine, the source of the lubrication, so that's the boundary layer of the film, usually between 2 and 10 microns, that's deposited on the cylinder wall. The source of that film is oil splashing up from the crankcase. And you have a wiper ring that maintains that film. Now, the problem with this method is that when the cylinder pressure is very high, for example, in one of these compound cycle diesel engines that we're trying to build, that is the NASA compound cycle program, when the cylinder pressure is too high, the that layer, that oil film, effectively is wiped off, right? Because the oil has nothing impedes the oil from flowing down or flowing up, so it's basically squeezed. Imagine you have a puddle of water on the floor, and you take a leaf blower and you blow on it, right? You're going to displace it. You're going to push the oil down. You're going to create like they call it I think like when a helicopter hovers over the ocean, it'll do this. It'll create this this concave surface on the water. And this is basically what's happening to the oil film. So this oil film is being quite brutalized in the engine, and so you basically have no choice but to accept a very, very thin layer. And so the wear on a typical engine is highest when you have the very high cylinder pressure, and it's at the top dead center. So it's what they call the ring reversal point. So that's like the point where when the injector begins to squirt fuel, the pressure rises extremely rapidly to about 200 to 250 bar, and the oil layer is reduced to its minimum thickness. And on the compound cycle program, this was the limiting factor for ring life. I mean, of course, you can use ceramic materials or cermets or all sorts of very exotic alloys, but the fact of the matter is, you ultimately still limited by the pressure that the gases are producing. Notwithstanding, of course, the very high temperature, which breaks down the polyphenol ethers that are used in these kinds of high temperature applications. Of course, we should also mention that because the operating temperature of this engine is going to be very high, to create more cylinder pressure, you have to inject more fuel, and so when you do that, of course, you're going to have very, very high oil operating temperature, and the viscosity of that oil is going to be very low, right? Because of viscosity. Temperature coefficient, or viscosity, will decrease with temperature, which is not compensated by the increase in pressure. So in fact, the oil is being compressed by the combustion gases circumferentially, but that's not enough to keep its viscosity sufficiently high to maintain a good film. And so turns out there's actually a really simple solution to this problem. What you actually would do is simply put what I call a telescoping oil stem that would reciprocate in the crankcase into a cylinder that's pressurized. It delivers it hydraulic fluid, pressurized it above the background pressure, so above the pressure of the actual peak cylinder pressure. So if you fire, say, the engine at 300 bar, which is possible, right? I mean, right now I think the Germans have gotten to like 250 bar. I think what's his name? That guy there, Banks Power. I think is that they got the Duramax to like 240 bar, and so because I'm designing a two-stroke diesel engine, I think that can take I'm designing for like 300 bar, 7 horsepower per cubic inch is what NASA actually achieved. And of course, the application for it is obvious, right? Light air mobility vehicles, jetpacks, things like that, light helicopters. So the goal of Christoph-Terry Energy Technique is simply to replace the gas turbine, and for small applications, right, where the gas turbine is very inefficient, and also to create a new power plant that can be used for these applications that presently are devoid of any kind of suitable power plant option, right? Think of like a jetpack. If you want to build a jetpack, you can't just call up Honeywell and say, oh yeah, I need a super lightweight, very efficient engine. It doesn't exist. The technology simply doesn't exist, but it's possible, right? There's nothing forbids you in physics or nature from creating a more power dense engine, provided you have the suitable materials and engineering. So this is ultimately the objective. So yeah, some design details. So the oil stem reciprocates inside of the oil stem is a piston, basically a very long piston. It has a seal and it reciprocates inside of a cylinder, which is pressurized with oil. And so every time the engine fires, so at top dead center, when the ring begins to reverse, the oil is pressurized to above the background pressure, and it squeezes oil out, and gives it a very nice hydrodynamic lubrication regime, rather than say mixed. There's three kinds of lubrication regime. There's sort of asperities, mixed lubrication, and then of course a boundary layer. So you want to have boundary layer for something that, if you want something to last very long, you need to have a full boundary layer lubrication regime operating at all times. And are there disadvantages of this design? Well, I mean, certainly there are, but again, it's one of these things where it's like you want a radio, you need an antenna, right? You don't really talk about like do antennas have disadvantages? I mean, they might, right? They cost money. They take up space. People don't like the way they look. They're difficult to maintain. People get killed maintaining them, right? In fact, people are falling off antennas like every day. It's very dangerous. But you need one, right? If you want to talk to your friend or whatever across the country. So I mean, that's how I look at it. It's like, okay, well, you don't have to like this technology. I'm not forcing you to like it, but do you want a small light air mobility vehicle that can fly for 3 hours and burns the same amount of fuel as a typical diesel engine in a truck, but weighs even less out of a gas turbine, right? That's pretty amazing technology. I just can't think of anything that ultimately wouldn't. I couldn't really think of any other option. I mean, you can miniaturize a gas turbine. I've extensively investigated that, but the problem with doing that is that you have to use ceramics, and ceramics are very brittle. And I mean, you can make a recuperated gas turbine, and it's all fine and dandy at 100% load, but you drop down to 50% load when your light air mobility vehicle is burning through fuel, and then your aircraft's now lighter because fuel takes up half its weight, and now you have less load on the ducted fan, and as a consequence, your diesel engine has operating at less load, and that's fine because efficiency is not very much dependent on load. The efficiency of a diesel engine is only weakly related to its load, whereas a gas turbine is, because it's aerodynamic, once you are outside of that optimal velocity window, the gas turbine is very ineffectual, unless you have it like an adaptive gas turbine. You actually change the angle of attack of each blade or whatever, which has been considered. They consider this for tilt rotors, because tilt rotors have this inherent problem that they want to make a lot of thrust on takeoff, but then during cruise they want to slow the rotors down. But that hasn't really worked. But yeah, that's the main idea. This is really the enabling factor, because we can push that NASA compound cycle diesel engine to power densities that the guys at NASA would have only dreamed of. So it's very exciting technology, and certainly patenting it, I think it could be worth many millions, if not billions, because it also has a lot of applications in, say, ship propulsion. It's a greatly enhanced power density package. I think a lot of people would find very, very interesting, very useful. Unlike a lot of these modern innovations like batteries, like literally going back in time in terms of power density.